In the last segment, we saw an incredibly powerful equation, sometimes called the Nernst equation, that connects together Gibbs-free energy and equilibrium, thus bringing together the ability to understand spontaneity in the context of both temperature and pressure, or concentration. In this example, we're going to look at applying that equation. So let's look at a chemical reaction. If you mix together bromine gas and chlorine gas, they will react together to make a bromine chloride. In essence, they'll trade partners. So the question is the reaction written above spontaneous if we have 0.120 bar each of our Br and Cl gas and 0.240 bar of product? This is very much the kind of problem that you might run into. You have some concentrations of reactant and product at a particular temperature. In this case, we're at 298. And the question is this reaction spontaneous? Now, we will need a little bit more information to answer this question. We need our delta G naught F values. Remember, the equation we had allowed us to modify delta G naught for a reaction to account for temperature or pressure and concentration changes. But we do still need to know that original delta G. In this case, I looked these values up in our book's appendix. You'll also notice that our chlorine gas has a delta G naught F of 0 because it is in its standard state. Using this, we can calculate our delta G naught of reaction. If you don't recall how to do that, you should look back in the last chapter and refamiliarize yourself with calculating delta G naught F. So you can see we get a delta G naught for this reaction of negative 4.90 kilojoules per mole. Now, last chapter we would have looked at that and said, great, negative delta G, this is spontaneous. However, we're not dealing with compounds that are present at 1 bar. And what's more, even though this may favor our products, we currently have more products than reactants. So that means we've run into a bit of an issue, at least based on what we used to know. We need to adjust this for our new temperature and pressure. So let's do that. We know that we need to calculate our Q next. To do that, we need our expression for Q. In this case, that means the pressure of our BrCl squared divided by the pressure of our Br2 times the pressure of our Cl2. We can fill in for our given values. Remember, these numbers are made unitless in a reaction quotient because we're dividing by the standard state of each. That gives us 1 bar, which gives us a reaction quotient of 4. The next thing we're going to need to do is to plug this into our equation. We have most of the information we need to plug into this equation to find our answer. We know our temperature, our Q, and our delta G. We do need our ideal gas law constant, however. Here's where things get a little bit odd. Our units were in bar, right? So you might think that we need a number that's in terms of pressure. However, delta G naught has units of kilojoules per mole, and our temperature has units of Kelvin. That means that we need a value of R that has units in kilojoules per mole Kelvin. This is the kind of information that you could look up on your table of constants, and it happens to be 8.314 times 10 to the negative 3 kilojoules per mole Kelvin. So with that, we're ready to fill everything in. Our temperature, 298 K, we have R, and we have Q. If we fill those in, we're going to bring in our negative 4.90 kilojoules per mole. These values brought together give us 3.43 kilojoules per mole. And our result here is thus negative 1.47 kilojoules per mole. So this reaction, under these conditions, is going to be spontaneous.